We want to compute the forbidden space of an obstacle, and we're going to do so using Minkowski sums. So what is a Minkowski sum? A Minkowski sum of a set S and a set T is simply the combination of every point in S and every point in T and taking their sum. So the Minkowski sum of S and T is taking any point from S, any point from T, and adding them up. In this example over here, if you, for instance, take this point of T, which in this example actually is 0, 0, and I combine it with this point in S, okay, 0, 0 plus that point simply leaves it there. If I combine that point with anything in S, I still keep S, but that is not the case for any other point in T. If I take that point down here, combine it with this point in S, I will get a point down here. More generally, if I combine this point of T with anything in S, I will get kind of a shape, a translated version of S here. And even more generally, if I combine everything in T with everything in S, I will get this pink shape as shown here. That's a Minkowski sum. What we need also is an inversion. That's simpler. The inversion of S is simply taking every point of S but then minus. It's like taking S and then reflecting it about the origin. So why did we define all this? Because now we can describe the forbidden space, namely the forbidden space of an obstacle P is P, the Minkowski sum of P and the inversion of the robot. So why is that the case? So let's first remind us how we can, how the forbidden space is defined. I mean, the forbidden space is any configuration xy such that the robot at that configuration intersects the obstacle. Yeah, Rxy intersects P. So why can we describe the forbidden space like this? Because if we have a point, let's say we have a point xy in the forbidden space, what does that mean? It means, okay, it means that Rxy intersects P. That means there is a point in R0, 0, such that translated by xy, it lies in P. So Q plus xy lies in P. What does it mean that it lies in P? There is a point P in P which is equal to that. So let's write it like that. So this equals P for some point in P. Okay, now we're already nearly there because now I just take the Q, bring it to the other side. Okay, I can also write it in the following way, P plus minus Q. So now I have xy is in the forbidden space exactly if xy has this form, meaning it is a P and P, and this minus Q is in minus R00. And that's it. So we now know that we can describe the forbidden space as a Minkowski sum. That means we can also compute the forbidden space if we can compute Minkowski sums. And for this, we're going to make some observations about Minkowski sums. First of all, the following. So let's say I have two sets or two objects P and Q. In my example, instead of having Q, I will have this R for the robot. But the observation, I use P and Q. So the extreme point of PQ in some direction D, so here I have a direction D and I want to know what is the extreme point in that direction. So if I take the orthogonal line through to D, what is kind of the last point that this line touches, which is here, more or less. This is the right line. Then that point, the extreme point in the direction, is the sum of the extreme points of Q and P in that direction. So here my example, it's R. The extreme point in that direction is this point. The extreme point for P in that direction is that. So I know that this extreme point is actually the sum of R and P. And why is that the case? I mean, firstly, R plus P, obviously because R is in R and P is in P, the sum is part of the Minkowski sum. So I know that this point is in the Minkowski sum. But I also know that if I now take any other combination of a point here in R at a point P and P, because R is further in this direction than this other point, and P is further in that direction than that point. Also the sum is further direction in that direction. Okay, so we have this observation, and this immediately helps us to say something about the Minkowski sum of convex objects. So let's do that. Let's say I have two convex objects, P and Q. They have M and N edges, and I want to know how many edges does the Minkowski sum have. Is it the sum, M plus N, or is it the product, M times N, or the maximum of M and N? The correct answer is it's at most M plus N. So why is that the case? Because essentially anything that is extreme in a certain direction is a combination of an extreme point on the one object plus an extreme point on the other object. So if I have an extreme, if I pick a direction, then on that one object, it's either a vertex that is extreme or an edge, and I combine that with a vertex or an edge of the other one. So all of the extremes are combinations of vertices and edges, or possibly edges and edges, or vertices and vertices. And also they occur in the order in the order in which they occur on R and P, and also even more strongly if you think of, so if I now order all of the edges, so of R and P, we see that the edges actually occur as in the order, in that order. So here we have this extreme point which corresponds to the extreme point. This extreme point corresponds to this plus that. And then the first edge is the first edge that comes in this order. So it's this edge. Then the next one in that order, I mean, this one is further around, so this one is the next that shows up here, and so on. This also directly gives us an algorithm which we can use to compute the Minkowski sum of two convex polygons in linear time, so in time m plus n. And that is simply, I walk around both polygons at the same time, using this angle as criterion for where I step further next. And then I can simply add the next edge. So let's make that specific. I have the vertices of P in counterclockwise order, the vertices of W in counterclockwise order. Now I'm going to process the edges P and R in the merged order in terms of the direction with the x-axis. So I start here and here, let's say, because this is the first one. This is the first edge in terms of that order, and this is the first edge of R in terms of that order. And now I'm processing the edges in the merged order, so this edge comes first. And then I simply take the edge that I get by taking that edge plus the current vertex here, or stated differently, I'm going to add Vi plus Wj and move further on the one that comes next in that order. So this would be V1 plus W1, and then here for P I go to V2 still plus W1. The next in that order is this edge, so then I take W2 plus V2 and so on. And in this way I get this polygon. And this gives me a linear time algorithm to compute the Minkowski sum of P and R. Now this allows me to compute the forbidden space of one obstacle, but what we will need is the union of those forbidden spaces, and we're going to see how to compute that next. We've seen that the forbidden space of a convex obstacle is, or can be described as, a Minkowski sum. Now we're going to look at the union of obstacles, or union of convex obstacles. And for that we will first going to look at this concept of a pseudo-disc, or a set of pseudo-discs, because pseudo-discs have to at least come in pairs. So two planar objects P and Q are a pair of pseudodiscs if their intersection pattern is like the intersection pattern of two disks. So how can two disks intersect? First of all, two disks might not intersect, that's one option. But if they intersect, so if I have one disk and another disk, if they intersect, we will always have the case that this disk, it enters and it exits again, but it won't enter and exit again. And of course, you could also have the setting where the disk, the intersection is like this or like that. But essentially, the important part here is that if I look at the boundary, it's of one in the intersection of the other. That's a connected piece. And that's different from the setting of ellipses. So if I have ellipses, the boundary here might be two pieces. But that cannot happen for a disk. And that's why we call P and Q pseudodiscs if the boundary of P intersected with the interior of Q is connected and the boundary of Q intersected with the interior of P is connected. So if I have pieces like this. So a set of pseudodiscs is a set of objects where every pair is a pair of pseudodiscs. And we need one more concept, namely point P, which is on the intersection of P and Q, is a boundary crossing if delta P, so the boundary goes from the outside to the inside at that point, or inside to outside. So that means we have a setting, let's say like this. This is a boundary crossing. In contrast, no, if they intersect here, this would not be a boundary crossing because P stays inside. Oh, if it's that one, it stays outside. Okay, so that's a boundary crossing. So how does that relate to our setting? We have the following. If we have two convex polygons, P and Q, and we take the Minkowski sum with yet another convex polygon, R, and R will in our case take the role of the inversion of the robot, then the Minkowski sum of P and R and the Minkowski sum of Q and R, those are a pair of pseudodiscs, meaning the intersection pattern is like for disks. So let's illustrate that. So let's say R is a square like that. I have P here, let's say. Now the Minkowski sum might be something like this. And if I now have Q, let's say like this, then the Minkowski sum with R will look like something like this. And as you see, the boundary here is connected and the boundary here is connected. Why is that the case? It is a case because if we look at the extreme points of P and Q, so here we have Q, here we have P, the extreme points, if I have two convex polygons, have the following properties, if I look at who's extreme, P or Q, in the space of directions, then in these directions, P is extreme. Then in these directions here, Q is extreme. And we only switch once from P to Q. And we can only switch once from P to Q because, so let's have a drawing here. So here we have P and Q, and as I kind of illustrated in the space of directions, here Q is extreme, there P is extreme. And if that would be different, so if Q would be extreme here and here, so if I would see Q here, and I would see P here and here, then it would mean that because they're convex, all of this is in Q, all of this is in P, meaning that they would need to intersect. What does that mean in terms of the Minkowski sums? It also means that the Minkowski sum, if I take the Minkowski sum of Q and R, the extreme points of the Minkowski sum of Q and R are extreme points from Q plus extreme points of R. So that Minkowski sum will be extremal here. The Minkowski sum of P and R will be extremal here, meaning what I'm going to see is something like that. Then I can switch over and I can only switch once back. So it cannot happen that the Minkowski sum shows up here again, because then that point would be extreme. Okay, so we now know that the Minkowski sum of P and R and the Minkowski sum of Q and R, those are pseudodiscs. How does this help us? It helps us in terms of bounding the complexity of the union of the forbidden spaces. And for that we have the following theorem. The union of a set of convex polygonal pseudodiscs with n vertices overall will have at most 2n vertices. And the argument that we're going to use here is a charging argument. So we're going to look at the vertices of the union. And this is also a vertex of the union. Let me color it differently. This is also a vertex. And here, this one, and so on. Now I want to count these vertices. And in a charging argument, I will charge these vertices to vertices of the original polygons. And in this way bound the number. And as you see, I want to show that my union has at most 2n vertices. To make this work, I will want to make sure that every input, every vertex of my original polygons gets at most a charge of 2. So what charge do they get? So some of my vertices of the union are simply vertices of the input. They will charge to themselves. The critical ones are the boundary intersections, where I go from inside to outside for both. And what I want to do there is simply I'm going to charge the first vertex that I see inside. And in this way, as you see here, this blue one would get a charge of 2. Let me show that here. Everyone gets a charge of every vertex starts with a charge of 1. I want to show that my charging scheme gives everyone at most a charge of 2. If I'm outside or if I'm on the boundary, I simply charge myself. If I'm by boundary crossing, I'm charging the next one inside. Okay, so what could go wrong? The only thing that could go wrong is that there isn't one in the inside. I mean, if there's one in the inside, it can get at most a charge of 2 because it will be charged at most from 2 sides. But there could be the situation we have a boundary crossing and there's no vertex here. So why wouldn't there be a vertex? Because this polygon comes back, and this is a straight edge, let's say, comes back before there's a vertex. Okay, it's enough if I can charge on one of the 2 polygons, so then I will charge here. But it could also be the case that there's no vertex here, so that this one immediately crosses through that polygon. But what does that mean? It means these 2 are not pseudodiscs. So for pseudodiscs that cannot happen, so I can always find one inside. So here in this example for this boundary crossing here, green does not have one inside, but blue does. And because we have pseudodiscs, we can always find such a vertex inside, which we can then always charge. Every vertex gets at most a charge of 2. We have at most 2n vertices. What have we seen so far? We've seen that if we have convex robots and translations, we can actually now handle the problem in the following way. So the obstacles might not be convex, so we're going to triangulate the obstacles, because then we have convex obstacles by simply taking the triangles as obstacles. We know how to do that. For each such obstacle, we then compute the forbidden space. Now we need to take the union. Okay, and that's kind of the tricky part there. The way we're going to do it is take all of these forbidden spaces, divide them into two sets. So half of them here, half of them there. Recursively compute the union and then combine. And the combine we do in the following. We use the map overlay algorithm from the line segment intersection videos. That also allows us to compute the union of 2 objects. Then, to get the roadmap, we compute the vertical decomposition, compute the roadmap on that, and we're done. So what is the running time of this algorithm? More specifically, what is the running time if the robot is convex and has constant complexity. So think of a rectangle or similar. So is the running time n log n log squared n, or n squared log n? And you can always think of these running times as being expected. It is order of n log squared n. Why is that the case? So let's have a look. Triangulating the obstacles, we have seen an algorithm that runs in order n log n time. This can actually be done in linear time, but we've seen n log n, and that is enough for our purpose. Now we compute C of p for every of the resulting obstacles, or for each of the triangles. So complexity, if I have a triangle and the robot, the complexity of that will be, because the robot has constant complexity, will be 3 plus that constant. So I have lots of configuration space obstacles or forbidden spaces of constant complexity. For each it takes constant time, and the number of triangles is linear, so overall this will take linear time. Now let's skip the next step for a moment. The vertical decomposition, because we have the union of pseudo-discs, it has linear size, and then computing the vertical decomposition will take expected n log n time, and then computing the shortest path in the roadmap will take linear time. So the interesting part is computing the union. For that, we use the plane sweep as we used it for the line segment intersection, but we do so always, to combine two unions of forbidden spaces, and we do that divide and conquer. So first we split the problem into two halves, so we have t of n is 2 times t of n half. So now we have computed the union of one half, the union of the other half. We want to combine it, and this will be then of order. So the algorithm that we've seen was n plus k log n. So k is the number of intersections. That also corresponds to the boundary intersections that are vertices also of the union. So we know that this is also linear. So we know that this is of order n log n. So we have a recurrence 2 times t of n half plus order n log n. So you can use recursion trees. You can also use an extended version of the master theorem to see that this exactly solves to order n log squared n. So that is what we have so far. If we have a convex robot of constant complexity translating among disjoint polygonal obstacles, overall having n edges, then we can pre-process in n log squared n time expected, and then later find a collision-free path in linear time. So this was now for constant complexity convex robots. Let's see what we get if the robot is more complex, or more generally what Minkowski sums, the complexity of Minkowski sums, if we are not looking at two convex shapes. So if we have two convex shapes, P and R, we know their Minkowski sum has a complexity, the sum of the complexities. If one is convex and the other one is not convex, then we get the product. If both are not convex, we get m squared times n squared. Let's go through these three cases. The first one we've already seen. We had this argument with the extremal point that gives us m plus n. Now for the second case, so for the m times n, we've already used this construction actually in the previous algorithm, where we simply said, okay, if I have something convex and something that is non-convex, I can take the non-convex object, triangulate it, and then take the Minkowski sum of that object with every triangle. And that is then also the way that we get an upper bound of m times n by taking the Minkowski sum of R, which is convex, with each of the triangles and taking the union of that. The triangles have constant complexity. R has complexity m now. So the sum, using the m plus n gives us m plus 3 for each. We have a linear number of triangles that gives us m times n. And here, this is just an example where you actually get this as complexity. So this is R, you have P is in blue here, and the union has, so the Minkowski sum of R and P is this pink shape, and that indeed gets m times n complexity. If both are non-convex, we do the same trick. We triangulate, but now we have to triangulate both, and that ends up with this m squared times n squared. And in the book, or here also on the slide, you see an example where you actually get the m squared times n squared. So much about translating robots for now. Next, we're going to also look at rotation.